Hello everyone, welcome to this video titled Checking Solutions to Inequalities. In this video, I'm going to be going over 5 examples taken from the adaptive practice at a website called ck12.org. And this adaptive practice comes from their Algebra 1 text. All right, so here we are in the adaptive practice for checking solutions to inequalities in ck12.org's Algebra 1 text. And like I said earlier, I'm going to just be going through 5 of the 10 examples here in this practice. I would highly recommend you do this yourself after reading the text, of course. And even after you're done with the 10 examples, you can always go back in and do more practice if you wish. And I would highly recommend too, while watching this video, whenever I start a new example, pause the video and try to work it out yourself, just before you see how I do it. Okay, so we're starting off straight away. We're asked to solve an inequality. Now, whenever you're asked to solve anything, right, you're trying to find or describe, what values can the variables take, right, the letters, so that the statement is a true statement. So my inequality here is x divided by 5 is less than or equal to the number 6. So what numbers, would make this true? So I'm going to write this in my scratch pad. So we have, again, x divided by 5 is less than or equal to 6. All right. Now, the way you solve a linear inequality, right? This would be considered a linear inequality because, our variable here, x, is to the first power. And, it's not in a denominator. It's not in any special symbol, so this would be considered a linear inequality. To solve a linear inequality, you follow pretty much the same steps that you follow to solve a linear equation for a particular variable. But there's just one real key thing you got to keep in mind, though. All right, so whatever you do to one side of the inequality, do to the other side of the inequality as well, right, when you're solving. The one thing you need to keep in mind is this. All right, so I'm going to write off the side here a property of inequalities that you really need to keep in mind. So when you add something to one side, you add it to the other side. When you subtract something from one side, you subtract it from the other side. When you multiply or divide, by something on one side, you do it to the other side as well. But it's in this multiplication and division, you got to be careful. Okay, so I'll write this property over here. If, say I have an inequality, A is less than B or greater than, or is less than or equal to, or is greater than or equal to. Okay, but I'm just going to write up this inequality here. If A is less than B and C has some negative number, so say C is, less than 0, right? C is negative. If that's the case, then when you multiply or divide both sides by C, A times C or divided by C, remember that division is just multiplication by the reciprocal. If I multiply both sides by this negative number, what happens is the inequality symbol flips around, changes direction. So here I'm starting with, A is less than B. That when I multiply or divide both sides by a negative number, that becomes is greater than. So I'm going to point that out. I'm going to highlight this with a different color and say, the inequality symbol flips around. Right. Now again, this is only when we multiply or divide by a negative number. Right? When you multiply or divide both sides of an inequality by a negative number, the symbol will flip, will change direction. Otherwise, adding, subtracting, multiplying by a positive number, none of that changes the symbol. So please be aware of this. All right. So back in this example, right, we have x divided by 5 is less than or equal to 6. And I would like to get the variable x by itself to describe all the numbers I can replace it with. So on the left side and right side, let's go back to the original color. So what I'm going to do here is, here's the left side of the inequality. And then here's the right side of the inequality. Right? To get x by itself, it's being divided by 5 right now. The inverse of that, to undo that, I'm going to multiply both sides by 5. Now, when you multiply, I said this earlier, right? When you multiply both sides by a positive number, the inequality symbol does not change. Right? There is no change here. I'll say no change. Okay, because I multiplied by a positive number. So now at the end here, the left side, the 5's cancel. You have x is less than or equal to, and then on the right side of the inequality symbol, 6 times 5 is 30. And here we go, right? The variable is by itself. And what we have now is a description of the solutions. All the numbers I could replace x with and make the original statement a true statement. Now, what I'm going to do now is, the title of this practice is checking solutions to inequalities, right? So I am going to actually show you how we would do this, right? Let's take these numbers I've been describing here, right? All these numbers less than or equal to 30, and let's test some out. All right, so I'm gonna do some checking, right? So I'll just pick a few values, right? There are technically, infinitely many numbers being described here, right? All the numbers less than 30 or equal to 30, that's infinitely many. So there's no way I'm going to be able to check all of them. I'll just show you a couple. All right. So how about 30 itself? All right, what if x were 30, right? This said x is less than or equal to 30. So I plug that in to the inequality, right? We have 30 for x divided by 5. And is that less than or equal to 6? And then we simplify both sides here. 30 divided by 5 is 6. Is that less than or equal to 6? Yes, right? This is true because of the equal part, right? 6 is equal to 6. So it's less than or equal to 6. So this is true, meaning that 30 is a solution, right, which I have described here. X equals 30 is a solution. check a different value. All right, so I'm gonna just replace this here. So let's check a different value. Something else less than 30, like say 10. Oops. Actually get some pen work here. That's too thick. Let's do this. All right. How about 10? Right? 10 is less than 30 or equal to 30, but it's less than 30. If I put in 10 for x, right, now the left side looks like this. 10 divided by 5 is less than or equal to 6. 10 divided by 5 is 2, right? And is 2 less than or equal to 6? That's true, because 2 is less than 6. 2 is smaller than 6. It's to the left of the number line. 2 is left of 6 on the number line. Okay. And then here's one more that is a solution, right? So I'm just going to take a different value for x. All right. So this time let's take another number. Now this time, how about numbers less than 30? There's a lot of them, infinitely many. So how about say negative 50 or something, right? Any negative number is definitely less than positive 30, right? It's to the left of 30 on the number line. If I were to plug in negative 50 here, right, for x divided by 5, negative 50 divided by 5. Well, that left side now is, negative 10, and is negative 10 less or equal to positive 6? Absolutely, it's less than. If negative numbers are always less than positive numbers, right? They're to the left of them on the number line. So there's another solution, right? And I could do this all day long. Pick any number I want that's less than 30 or equal to 30, and this statement will be true. Now what I want to do, I just want to do one more of these just to show you when is something, not a solution. All right, so I'm keeping everything but the value of x. All right, so now, how about instead of picking a number, less than 30 or equal to 30, pick a number that's, the opposite of that, that's greater than 30. So like say, 35. What if I checked 35? So I'm replacing x with 35 so that, x divided by 5, 35 divided by 5, is that less than or equal to 6? 35 divided by 5 is 7. And then is 7 less than 6? No, it's greater than 6. It's to the right of 6 on the number line. Is 7 equal to 6? Absolutely not, right? I said it was greater. So what we have here is a false statement. So that means that our value of 35 here is not a solution to the inequality. All right, not a solution. And that would be the case whenever I chose a value greater than 30. All right, so that was a lot there. I'm not going to do this for every single example, but just to give you an idea as to what they mean by, checking your solutions. Once you've solved it, test some numbers out, see if you believe that you are correct. All right, so back in the choices, right? This is option B, right? All the values of x less than or equal to 30 will satisfy this inequality. Checking it out. Wonderful. And let's continue on. So this is the same kind of problem, right? Solve the inequality. They say using division, right? Because you see how on the left side here we have 9 times x. I would have to then, to get x by itself, the opposite or the inverse of multiplying by 9 is dividing by 9. Right, so let me pull up my scratch pad. We have 9x, right? 9 times x is greater than 81. And once again, here's the left side. Here's the right side. And notice, I'm not putting the inequality symbol yet because I don't know if it's going to flip around, right? And, left side, I'd be dividing by 9, or you could say multiplying by 1/9, right? Multiplying by 1/9. Right side, I'm dividing by 9. And, because this is a positive number I'm dividing by, the inequality symbol will not change. There is no change, no flip in the inequality symbol. So once again, the only time when you add or subtract or multiply or divide of those operations, the only time you're flipping the symbol is when you multiply or divide both sides by the same negative number. All right. Okay, so now we have the x by itself, right? 9x divided by 9 on the left is greater than, and then 81 divided by 9 is 9. And here we go. Right, the variable is alone on one side. X is greater than 9. So here are some examples of solutions. Right, here are some examples of solutions to this inequality. Right, x equals, now 9 doesn't work. Right, this is describing all the numbers greater than 9. 9 is equal to 9, not greater than 9. All right, so 9 is not a solution. But anything bigger than 9, 9.1 would be a solution. 9.05, would be a solution. 10 would be a solution. 100 would be a solution. 27 would be a solution. I could do this all day long. 1,578.543. Whatever. I can do this forever. There are infinitely many numbers greater than 9. So those are just some examples. And then back up here, right? Of the options, the one that actually describes the solutions to this inequality is D, right? X has to be some number greater than 9 to satisfy this inequality. Wonderful. All right, next example. All right, so this one, a little more complicated. But as I said at the beginning, in the first example, solving these, linear inequalities, right? See x to the first power here, and there's no, higher powers of x, higher powers of the variable. Solving one of these linear inequalities with one variable, I'm going to go through the same step that I would go through to solve a linear equation with one variable. But, keeping in mind, whenever I multiply or divide by a negative number, the inequality symbol will change, and that's the only time it will change. All right. Okay, so we have 9 times. All right. Now I could go through and all right. So I see the options here. Look at the question. Which of the following choices is a solution? They should have the word a here to the following inequality. So we're not actually asked to solve this, right? We're not asked to find all the solutions. We're only asked which of these 4 is a solution. Okay, so let's just do that. Right? I'm sure in a later video, I did see later in this Algebra 1 text, there will be a section where we go through all the steps of solving a linear inequality. So right now, let's just check. Is -2 a solution? Is 0 a solution? Is 2 a solution? Is 4 a solution? Okay. All right, so our inequality was, 9 times the quantity x plus 5. Right, x plus 5, and then I believe it was -3. Yes, and then is less than or equal to 24. the first option was -2. Right, so I'm going to check. We're checking, see if certain values are actually solutions, make this a true statement. All right, so first x equals -2. So I'm going to plug that in, right? 9 times, and then x is, replaced by -2. Now, the x is not being multiplied by any number other than 1. It's not being raised to powers other than 1. So I'm just going to put, usually I put parentheses around my replacements, but if it's just a single letter with a coefficient of 1, I don't. Then plus 5, and then -3, right? And then is this less than or equal 24? Let's see if this is a true statement. All right, so your left side, right, you're performing the order of operations. You're simplifying the expression, inside the parentheses first. -2 plus 5 would be 3, right? So it's 9 times 3 minus 3 on the left. And and then you do multiplication, for addition. So 9 times 3 is 27. And then -3 is 24. And is this less than or equal 24? Yes, this is true. Because of the or equal to part, right? 24 is not less than 24, but it is equal to 24. So we're lucky. This works, right? They asked us which of the following choices is, a solution to the inequality, and -2 is. Now, if I were to plug in 0, I'll just speak this one. If x were 0, 0 plus 5 is 5. 9 times 5 is 45. 45 minus 3 is 42. Is 42 less than 24? No. Is it equal to 24? No. So it's not less than, nor is it equal to 24. So 0 is not a solution, right? If x were 2, 2 plus 5 is 7. 9 times 7 is 63. 63 minus 3 is 60. Is 60 less than 24 or equal to 24? No, neither of those things. So 2 is also not a solution. And then for 4, 4 plus 5 is 9. 9 times 9 is 81. 81 minus 3 is 78. Is 78 less than 24 or equal to 24? No, it is not. So like I said earlier, we kind of lucked out here that the very first option was a solution. -2 is a solution. And again, that's not the only one. It's not the only one, but it does work, right? There are other numbers that would work here, like say -5, if x were -5, this left side would have a value of -3, which is, less than 24. So just be aware that most of the times you're seeing these, linear inequalities, there will be, infinitely many solutions. All right, so wonderful. Next example. Right, so once again, which of the following choices below is or are solutions to the following inequality? Hey, so you see in parentheses here, they got are or solutions. So there may be more than one. Right, there may be more than one. So we're checking 1, 3, 5, and 7. All right, well, just like the last example, I'm going to just kind of read these off. All right. When I plug in 1, right, 1 minus 8 is in parentheses, right? X minus 8 is in parentheses. So I would do that first. 1 minus 8 is -7. And then 6 times -7 would be -42. All right, and then -42 plus 14 would be negative 28. Is negative 28 greater than 2? No, a negative number is never bigger than a positive number. So 1 is not a solution. How about 3? Again, 3 in for x. 3 minus 8 is negative 5. 6 times negative 5 would be negative 30. Plus 14 would be negative 16. Is negative 16 greater than 2? No, it is not. So 3 is not a solution. How about 5? If x were 5, 5 minus 8 is negative 3. 6 times negative 3 is negative 18. And then negative 18 plus 14 would be negative 4. Is negative 4 greater than 2? Again, no. So I feel like the only solution then that's in this list, or remember there will be infinitely many. There are infinitely many numbers that should work here, but the only solution that's in the list will be 7, it looks like. You know, if x were 7, 7 minus 8 is negative 1. 6 times negative 1 is negative 6. And then negative 6 plus 14 is positive 8. Is 8 greater than 2? Yes, it is. Right. So 7 is the only one of these that's actually a solution to that inequality. All right, wonderful. All right, and then finally, like I said at the beginning, I'm only going to be doing 5 of these, right, and leave the rest for you to do. And again, you can keep practicing after you do 10. You can practice to your heart's content. All right, here you have $439.27 in your checking account. You need to write a check for $521.15. What is the least amount of money that you have to deposit in the checking account so the check can clear your account? Right, so that's the unknown quantity here, this amount of money we need to deposit. I will call this B for deposit, right? It's just like any word problem. I'm reading through it, and then I try to identify unknown quantities, right? What are the unknowns? And usually they'll be they'll be pretty obvious in shorter problems, right? There's not too much to read, like this one. And once you've identified the unknown quantity, right? The amount, this amount of money, right? Amount of money to deposit in the checking account. I'll just say amount of money to deposit. Well, instead of writing this amount of money to deposit all the time, I'm just going to represent that with a single letter. And I said I was going to represent it with D earlier, right? Okay, so I've identified some quantities, right? Well, just one quantity here. And then we read back through and try to set up some sort of equation, or I'm assuming here we're going to set up an inequality to help us solve the problem. Now, we would like to have, 520 at least, right? You need to have at least $521.15 in the checking account for the check to clear. All right. So I'll write that out, right? We need the account to have at least, all right, that's the smallest amount we can have, at least, what was it, $521.15. All right. Now, at least means this much or more, right? We need $521.15 or more in the checking account for the check to clear. So I'm going to write that. This means greater than or equal to. I need the amount in the account to be greater than or equal to $521.15. And what do I have in the account? Right? What on the left side of my inequality here, what do I have in the account? Well, we have the initial $439.27, and then we're going to add more to it. We're going to deposit this B dollars, all right? So on the left side of the inequality, right, the amount I have in the account, I have the 400, and I've already forgotten what the amount was, sorry, 439.27. So $439.27 is in the account already, and we're going to add to this, right, plus a deposit, which I called D. And now we're solving this, right? We're solving this for D, right? They asked us, what's the minimum amount of money needed to deposit? I need to deposit at least this much for the check to clear. Now, I hope you can see that this would involve subtraction. I mentioned before, solving these linear inequalities, very similar to solving linear equations. If I want the B alone, right, it's being right now it's added. $439.27 is added. So I'm going to subtract $439.27 from both sides. 439.27. All right. And remember earlier, when you add or subtract, right? We didn't do any examples of this yet, but I said this earlier. When you add or subtract the same number to both sides of an inequality, nothing changes, right? The inequality symbol does not change. There is no flip. It's only when you multiply or divide by the same negative number on both sides. All right, so now on the left we have this deposit amount B is greater than or equal to, and then let's go through and subtract these. I'll do it the long way with the borrowing and everything. Can I do 5 minus 7? No. So I'm going to borrow one of these, make that a 0, right? Make this 15. 15 minus 7 is 8. Can I do 0 minus 2? No. So I borrow from the next space over, right? That becomes 0. This becomes 10. 10 minus 2 is also 8. Can I do 0 minus 9? No. So I borrow from the tens place, right? So 10 minus 9 is 1. Can I do 1 minus 3? No. So I borrow from this, the hundreds place. That makes that 11. 11 minus 3 is 8. And then 4 minus 4 is nothing. And then there we go. Okay, here we have it. Put a little dollar sign. Remember what that meant. D was a deposit amount. So what I'm seeing here is that in order for the check to clear, right, in order to have enough money in my banking account, my checking account, to write this check for $521.15, I need to put in a deposit of at least $81.88 to have to have enough money. So I'm gonna put that here. Now I don't know if I have to put the dollar sign. Well, let me see. I'm gonna put the dollar sign because unit should matter. So $81.88 is the least amount I can add to be able to have that check clear. Wonderful. So I'm glad they're doing that here where you have, so it should be important to put the correct units on your numbers, right? Units give numbers meaning, and this is a dollar amount. Wonderful. All right, so that's it, right? These 5 examples I'm going to run you through. You can work on the rest yourself. even practice more beyond that. Of course, I'm hoping you're reading the Algebra 1 text from ck12.org as well before you start practicing, work through examples, take notes, and all that. And I'm hoping this video helps you out when you're working on the adaptive practice yourself. All right, and thank you very much for watching.